Hello, welcome to Team 5's briefing on our implementation of path planning and peer pursuit control. In this lab, our goal is to solve one of the most fundamental problems of robotics, which is how do you get a robot to move from one position to another, given certain obstacles in a map. In this case, we were given the map itself, so that eliminates some of the complexity of needing to generate the map as the robot moves around its environment. So there were a few different steps that we needed in order to fully solve this problem. The first step was to localize the robot's current position. And this was what we did with our particle filter in Lab 5. The second part was, given the robot's current position and a goal position, to generate a path that would avoid the obstacles in its way. And then the third part is to actually control the robot to follow that specified path. So Gongi will first talk about how we implemented the path planner.
Thanks, Andy. Now the particle filter gives us a pretty nice abstraction for the path planning algorithm. We simply need to take a map, a starting post, and a goal point, and produce a set of waypoints describing the shortest path to the goal. We'll call this a trajectory, and here's an example of one. The red rectangles are obstacles, and the gray circles are the waypoints. Now the line segments connecting the waypoints should not pass through any walls, and the sum of their lengths should be minimized. Our team decided to take advantage of grid search algorithms, because they're more consistent than tree search algorithms. Although the latter may be faster, reliability rather than speed was our main goal. As such, we need to process the map into a Boolean grid of passable squares. We use 350 by 350 to limit the computational cost of the search. Then we dilate the map so we avoid squares which are close to walls. Now we're left with the problem of finding the shortest path between 2 points in a grid. Breadth first search is a fast option, but we can't handle edge weights with it, which will come in handy later. We actually used the less popular but useful shortest path faster algorithm with expected complexity of n squared. We noticed that the more edges we had between grid squares, the more natural and less grid-like our path would look. Compare the paths from 4 neighbors, 8 neighbors, and 15 neighbors. Note that these edges have to be weighted by Euclidean distance, so BFS wouldn't be useful here. We ended up choosing 15 neighbors for our final case. Now Nadia will introduce the pure pursuit control.
Thanks. Once we have a trajectory, we need to control our agent to follow it. By subscribing to the two nodes on the left, Path Planner and odometry data, we designed a pure pursuit node. It combines the current trajectory and agent post to update the published drive signal with every callback. The blue topics are used for visualization and debugging, and the green drive topic is what we set to accomplish in this lab. To do so, we implemented an algorithm which finds the point on the trajectory nearest to the car. Then, it iterates from that closest point until the final one and loops back over. We find the point where a circle with the look-ahead radius intersects our path. To drive to the final goal, we use controls to adjust the drive signal based on turning and velocity rates. To find the nearest trajectory point, we first create a parametrized vector equation of a line that connects two consecutive trajectory points, as shown in red here. By carefully selecting bounds for t, we obtain a set of vectors from the origin to points in the segment to represent it. Then, each of these output vectors is subtracted from the robot's location to give vectors that point from the robot to a point on the segment. We compile the possible vectors d in an array and compute their squared lengths. The minimum of those lengths would correspond to the minimum distance to the segment, which is shown in blue. Finally, we find the minimum distance to all trajectory segments and select the one which minimizes it. In other words, we choose the dark red segment that corresponds to the shortest length green vector. Thus, we find which of these line segments is closest to the robot by index. Kevin will now explain how to set a goal for the agent using the index of a segment that is closest.
Thank you, Nadia. Once we have the index of the segment closest to the robot, we look for the look-ahead point, which is the point on the trajectory that is a fixed distance forward from the robot. Using equations for the intersection of a line, the closest segment, and a circle, centered at the robot with radius equal to the proposed look-ahead distance. By only looking forward from the closest segment, we avoid issues like going backwards. Now that we have the look-ahead point, we applied pure pursuit as our controls method. In a pure pursuit controller, the steering angle is chosen such that the robot will reach the look-ahead point if the steering angle were kept constant, maintaining smooth travel. Now that we have implemented the particle filter localization, path planning, and controls, we can test the robot in simulation. Andrea will go over what did and did not work.
Thank you, Kevin. Our preliminary findings when integrating our pathfinder with the particle filter developed in the previous localization lab showed good results. We thought we could improve, as there were certain spots where a robot went off track, so we decided to increase the noise on the particle filter. This seemed to help with our initial localization lab, so we thought results would be similar. Unfortunately, the first loop performed similarly, while our second tested loop failed to follow the path given even more drastically than before. Through visualization tests, we determined our particle filter was faulty, and so we decided to employ the TA solution instead. When integrated with the particle filter given by the TAs, our results were significantly better than when integrated with our own. Thus, we decided these results were adequate and terminated our changes. Although our robot accomplished the goal of pathfinding and following, we still believe some improvements could be made. Through visual tests, we found our pathfinding algorithm to take more time than we expected to execute. For the future, we could test several alternate search-based algorithms or try sampling-based algorithms in order to compare their efficacies with respect to the problem we're trying to solve. Thank you for listening. We would like to ask a question to the staff. If your pursuit algorithm has a constant turning radius implicit in the implementation, we would like to know how we could modify our algorithm such that it travels straight to the first goal node rather than looping around to it upon initializing the start and goal nodes. We also appreciate the TA provided particle filter code, which we ended up using for our submission.